Now, categorical variables, however, are not always going to be just one variable. Okay? Sometimes we're going to be looking at two-way tables, such as this example that we have up here. So what the restaurants wanted to know was, depending on what type of music we play at the restaurant, does that have any effect on what the patrons or the customers in the restaurant will order? So can we predict what they're going to order based on what kind of music that we are playing? So this now is what we're going to call a chi-square test for homogeneity. The one good thing, I missed an I in there. The one good thing about this test is 4 steps, null and alternative. Are we allowed to do it? Check your conditions. Do it. Calculate your chi-squared test statistic. What does it mean? Find your p-value, write your conclusion. So the process is going to remain the same. However, now we are looking at a two-way table. So this is not a goodness of fit test like it was with the M&Ms or the dice or the hockey birthdays. Okay? This is what we're going to call a test for homogeneity. And the null is always going to be, there is no difference in the distribution of categorical variables for several populations or treatments. So there is no difference. The null hasn't changed. But now, how do I know it's a test for homogeneity and not a test for goodness of fit? Homogeneity goes with a two-way table. Goodness of fit is when we had just one variable. So here we have what kind of entree did they order and what type of music was being played at the restaurant. So we have a little graph here where you can see what's going on there. When they did not play any music, most of the people ordered other entrees, not French or Italian. When they played French music, well, most of the people ordered a French entree. And when they played Italian music, most of the people still ordered other. So there is no difference in the distribution of a categorical variable over several populations or treatments would be the null. And the alternative would be, yeah, there is a difference. Now, if you look up over here on the right side, how do we calculate the expected counts? Well, we don't know what they expect here. It's not like the other one where the company told us that 25% of their M&Ms were blue, or that we expected equal birthdays amongst NHL players. Here we're trying to test, are they all the same? Does it matter what music is played and what entree is ordered? So in any two-way table such as this, to find the expected count, we take the row total times the column total divided by the table total. So it's row total times column total divided by the table total. That's hard for me to say. So let's say I want to figure out what is the expected count of people ordering French food when no music is being played. So I want to figure out what is the expected count in this cell here. Well, to do that, I need to take the row total, 99, times the column total, 84, divided by the table total, 243. So my expected for no music and French cuisine equals 99 times 84 divided by 243, which is approximately 34.22. That's my expected count for the French and no music being played. Let's say I want to know what's the expected count for Italian music being played and they order Italian food. So I want to know this expected count. Well, it's the row total. So expected for Italian is the row total, 31, times the column total, 84, divided by the table total, 243. So I would expect there to be 9.57 entrees, or 9.57 people who ordered that. So that's how we take care of this expected count for a two-way table, a test for homogeneity, and we'll see soon we'll also have a test for association or independence. So again, the expected count for a two-way table is row total times column total divided by table total. All right, so let's take a look at an example for a test of homogeneity. The researcher wanted to know if people would have different responses depending on who the interviewer was. So for a class project, Abby and Mia wanted to know if the gender of the interviewer would affect the response to a question. The subjects in their experiments were 100 males from their school. Half the males were randomly assigned to be asked, would you vote for a female president, by a female interviewer? The other half of the males were asked the same question, but by a male interviewer. The table down here below is showing us the results of this study that they did. So they want us to state the null and appropriate hypotheses first. So remember, the null is always there is no difference. So in this case, the null hypothesis would be there is no difference No difference in what? Remember, we need context to every problem. So there is no difference in the true distribution of responses to this question. So there is no difference in the true distribution of responses to this question when asked by a male and female interviewer. So again, the null and alternative are much different here in chi-squared. Usually we're writing them in words. The alternative, I'm not going to write it out, but the alternative hypothesis would be there is a difference. Okay. Show the calculation for the expected count in the male yes cell. So part B wants us to show the expected for male yes. Well, the 30 is the observed for the male yes. The expected count, remember, it's row total times column total divided by table total. So if I do 69 times 50 and I divide that by 100, the expected was 34.5. And I would do that for all all 6 of these cells. So I would do it for male yes, male no, male maybe, female yes, female no, female maybe. But we're not going to do all of that work right now. Okay. Then part C says calculate the value of the chi-squared test statistic. So now we need to figure out what chi-squared is. Remember, it's the summation of O minus E quantity squared divided by E. So I have all my observes already, and I know that one of my expecteds is 34.5, but I don't have all of the other expecteds. So to do this, I would do 30 minus 34.5 squared divided by 34.5 plus, and then I would do that for every single one. It's a lot of work. It takes a lot of time. So fortunately for us, the calculator can do this these calculations for us. Okay. In stat test, guess what? There is a chi-squared test. So if we go to, we don't want a goodness of fit test. Remember, the goodness of fit is when we have one singular variable that we're looking at. The chi-squared test is the one that we want to use. And it's going to ask us to input the data into matrices. So our observed is in matrix A. Okay. So we need to go in and check out our matrices. So I'm going to go to second X inverse, which is matrix, and I'm going to edit matrix A. I'm going to put my observed in matrix A. So observed is matrix A. So we do not have to remember all of our matrix operations here like we did before. We just need to know how to input the data into a matrix, and it will do all the work for us. So matrices are always row by column. So the first number is always the row, the second number is the column. So in this one, we have 1, 2, 3 rows. So this is a 3 by, we have 2 columns. So it's always RC cola, row by column. So this is a 3 by 2. We hit enter and it says, okay, cool. What are the values? So 30 goes in the first cell, 39, 8, 3, 12, and 8 again. So now we've populated this matrix. Now we can try to run the chi-squared test. And the reason that we're using this calculator command of chi-squared test is it will do all of the observed for us. It's going to do all the work for us. You guys are really going to like this. So let's go back into stat test chi-squared test. Whoops, that's not chi-squared test. So stat test, I'm going to arrow up because it's shorter, to chi-squared test. And yes, my observed are in matrix A. And then I'm going to tell the calculator to do it. Calculate it. Huh, it did everything for us. It gave us the chi-squared test statistic. It gave us the p-value. It gives us the degrees of freedom. We haven't talked yet about the degrees of freedom for this, but we will. Okay. So this did all the work for us. We could have went and done these calculations like we did in blue on the screen all 6 times and found all 6 of these, which is probably good practice to start. But I wanted to show you how the calculator would do all that for us. So if we did this over and over and over again, we would get a chi-squared test statistic of 4.25. That's what this question was asking. Is that data statistically significant? Well, we haven't gone to the table and looked that up yet, but we'll do that in one of the next examples. First, let's take a look at the conditions and the chi-squared test statistic. Okay? Conditions, guess what? There's 3 of them. Random, they tell us or they don't. 10% is the population at least 10 times the size of the sample. Large count, are all expected counts the same? Are all the expected counts at least 5? The same conditions that we did for the goodness of fit test. That's nice. We don't have to remember separate conditions for tests for homogeneity versus tests for goodness of fit. This should say up here, this should say homogeneity instead of goodness of fit. Okay. Same exact conditions. Chi-squared test statistic, if you look down here, well, that's familiar. It's the same exact chi-squared test statistic that we've used previously. The only difference for a homogeneity is how we find degrees of freedom. Remember, for the goodness of fit test, for the degrees of freedom, we did K minus 1, or the number of categories minus 1. Well, for a two-way table, such as this one here, when we're looking at gender of the interviewer versus who they would vote for, to find the degrees of freedom for a two-way table, we take the row minus 1 times the columns minus 1. So if we look back at that 3 by 2 table that we just did for that example on the previous slide, there were 3 rows and there were 2 columns. So whoopsies, it should be row minus 1 times column minus 1. So it's 2 times 1. There are 2 degrees of freedom. Let's see if the calculator understood that. Yep, the calculator told us the degrees of freedom were 2. That's how the calculator came up with 2 degrees of freedom, by doing row minus 1 times column minus 1. All right, let's do an entire problem now for tests for homogeneity. Okay. So let's do the whole thing. Remember, anytime we do a problem like this, there's a 4-step process. What are we going to do? In context. Are we allowed to do it? Check conditions. Do it. Find the test statistic and the p-value. What did we just do? What does it mean? Interpret. Okay. So this problem says that the Pew Research Company conducts surveys about a variety of topics. One survey, they wanted to investigate how residents of different countries feel about the importance of speaking the national language. Separate random samples of residents from Australia, the UK, and the US were asked many questions, including, some people say that the following things are important for being truly survey country nationally. Some people say that the following things are important for being truly. Others say they are not important. How important do you think it is to be able to speak English? The two-way table summarizes the responses to this question. They're asking us, do these data provide convincing evidence at the alpha 0.05 level that the distributions of opinions about speaking English differ for residents of Australia, the UK, and the US? So I don't want to run a whole bunch of individual tests. This is where chi-squared comes in very handy, because it will allow us to see if all 3 of these countries are roughly the same. So remember, we're going to start every time with the null and alternative. So I'm going to number my steps here. We don't really need to do that, but remember, it's a 4-step process, every significance test. So what is my null hypothesis? There is no difference in the distributions of opinions about speaking English. Okay? There is no difference about the opinions of speaking English for residents of Australia, the UK, and the US. Guess what the alternative is going to be? There is a difference. I'm not going to write the rest of it out, but you would have to for a regular problem. You'd have to spell it all out for us. What kind of test are we going to do? Oh, our plan? We're going to do a chi-squared test. Oops. A chi-squared test for homogeneity, meaning they're all the same, homogeneous. Are all these countries, do they all feel the same about speaking English? Well, let's find out. So that's our plan. We're going to do a chi-squared test for homogeneity. The null is, no, there's no difference. The alternative is, yeah, there is a difference. Okay. So are we allowed to do it? I'm going to call this step 2, just to kind of simplify things a little bit. So is it random? Do they tell us in here how they gathered this data? Separate random samples, they told us. Nice. Makes it easier for us. They told us. Okay. The 10% condition, or is the population at least 10 times the size of the sample? So we have to make sure that that's true for each. So the 10% condition, there are more than 10,000 Australians. I'm sure there are. There are more than 14,600 people that live in the United Kingdom. Certainly there are. There are more than 10,030 people living in the US. Yes, we're good for the 10%. Okay. And then for the large count, are all expected counts greater than 5? Well, that I don't know yet, because I'm going to have the calculator find all of my expected counts for me. So before I can finish up this part of step 2, this large count, I'm going to go to my calculator and see what all the expected counts are. So this is a row 1, 2, 3, 4, column 1, 2, 3. So this is a 4x3 table. Well, let's think about that and how that would relate to our degrees of freedom. So if it's a 4x3, then the degrees of freedom would be 4 minus 1 times 3 minus 1. So it'd be 3 times 2. This problem has 6 degrees of freedom. Now let's go see if our large count condition has been satisfied. So I'm going to go in here to my matrix, which again is second x inverse. And I'm going to edit matrix A and tell it what size it is. Oh, we said this is a 4 by 3. Hit enter and it will do that for us. Now let's populate it. So there was 690 in the first cell, 1177 in the second cell, 702, 250, 242, 221, 40, 28, 50, 20, 13, and 30. Cool. Now, if you recall, we're going to go to stat, test, chi-squared test. Whoops. Stat, try again. Stat, test, chi-squared test. Enter. Yep, I put my observed in A. I've already entered it. Now I'm going to calculate. Oh, my chi-squared test statistic is 68.57. My p-value is tiny, and I have 6 degrees of freedom. Well, how would I use the table to find this p-value? Well, first I forgot. We need to make sure that the large count has been satisfied. So I need to see what were the expected values. When we run this test, the calculator does all the expected values for us. So all we need to do is go back into matrix. It puts all of the expected counts in matrix B. Whoops, that's not what I meant to do. So let's go back to matrix, edit, and let's go down to B and hit enter. That's all of my expected counts. Yeah, all of them are much larger than 5. So I'm fine there. So I can proceed now because I know that my large count condition has been satisfied. So what does that mean? All expected counts are greater than or equal to 5. So I know now that I'm allowed to do it. It's random. They told me that they randomly selected these people from these countries. 10% condition, yeah, there's certainly more than 10,000 Australians and 14,600 UK people and 10,000 30 US citizens. So we're okay there. And then we just checked that all of our expected counts were greater than or equal to 5. So now we're ready to move on. And in doing that, I kind of already have done all the work, right? So I let the calculator find the chi-squared and all that stuff for me. So let's go back and get that screen to come up. Stat, test, chi-squared test. Remember, this is not a goodness of fit test because that's for a one-way variable or only a one categorical variable. All right, and then calculate. And I have chi-squared test statistic equals 68.57. My p-value is 8.02 times 10 to the negative 13th. And I have 6 degrees of freedom. So if I wanted to use the table to find that p-value, well, I don't think that's going to be on there. Let's see what happened here. So we had 6 degrees of freedom, and the chi-squared test statistic was 68. So that's way out over here to the right. So the table, all it would tell me is that the p-value is smaller than 0.0005. But the calculator will give me the actual p-value. So if I were to do this by hand, which is totally fine, you'll get the same credit whether you do it by hand or by calculator. But if I were to do it by hand, I would say that my p-value is less than 0.0005. Is that significant? Well, that 0.005 or 8.02 times 10 to the negative 13th is way smaller than the alpha level of 0.05. Therefore, the data is statistically significant, and we have convincing evidence to reject the null and conclude that there is a difference about the opinions of speaking English for residents of those 3 countries. Since the data is significant, we do have convincing evidence against the null in favor of the alternative. So in conclusion, we just restate the alternative because that's the one that we have evidence to support. So we'd say there is a difference about the opinions of speaking English amongst these 3 countries. All right, we have one more type of test to look at, but fortunately for us, it's very, very similar to the previous 2 that we just did.